But now I think I will sort of start transitioning to our next speaker, which is Dr. Chen Sitan. So Dr. Chen is a assistant professor of computer science at Harvard, and he has a PhD in electrical engineering and computer science from MIT. And from my conversation with him, I can tell you that he's a very, very smart person who spent a lot of time researching and understanding a lot of aspects of theoretical computer science. And this is a talk I'm particularly excited about as well, just because I think, in general, a lot of people just without like a college education and things like that don't really get exposed to a lot of aspects of theoretical computer science. But I'm very excited for this talk, and I hope you guys are ready as well. So, yeah. I think you might not have screen sharing permissions, but if you just send like a request, I can approve it so that, okay, no, I think you got it. Okay.
Great. Should we get started?
Absolutely go for it.
All right. Yeah. Thanks so much, Adi, for organizing this event. This is, I think, an amazing initiative, and yeah, hope to share a bit about the kind of research that I work on, and more generally give a bit of an advertisement to this particular research discipline. I think this is something that, personally speaking, when I was in high school, I actually didn't really know that people worked on these kinds of things, and only first got exposed to this material in the first 2 years of undergrad. So hopefully I can make a pitch, and for people who are especially more mathematically inclined, I think this is a very exciting time to be working on problems at the intersection between theoretical computer science and machine learning. So let me just dive right in. So I want to begin by giving you kind of a 10,000-foot view on what exactly theoretical computer scientists study. I then want to give a quick snapshot of how to think about maybe research questions in machine learning as they fit into this discipline. I want to tell you what does it mean to do theoretical computer science for machine learning, and then I want to end with a vignette which will dive into some more technical content, but it'll give you kind of a flavor for the sorts of problems that you can apply some of this methodology to. So let's just start with theoretical computer science. So at a high level, this is an area that focuses on the mathematical study of the fundamental limitations of efficient computation. Okay, so what does that mean? Right, so at a high level, we're interested in questions of the following form. So let's say I have, some computer, or maybe I have, a data center, some kind of programmable classical computational device, and I'm able to run this for a reasonable amount of time. So on the order of, let's say, seconds, hours, maybe a couple years, but certainly nothing beyond, let's say, our lifespan or beyond the lifespan of the universe. Okay, so we limit to within some reasonable time budget for running this computer. And the question is, what can you do with this computer? And so to give you a preview of the kinds of things you'll see in, say, like a first year class on algorithms and data structures in college, you might learn about certain things like, what is the fastest way to sort, a very big list of numbers, right? And when we say fast, we really mean, I want to take as little time as possible to, given this large list of numbers, put them in the right order, right? We might be interested in something like perhaps a graph algorithm where, imagine you're trying to design an algorithm for Google Maps, right? So you want to tell the user if they want to get from point A to point B, what is the fastest way to do this? Okay, and people model this via something called the shortest path problem. And you'll learn, various algorithms for this problem that, again, try to optimize for, how long it actually takes to find this shortest path from point A to point B. Other questions you might encounter include, maybe I have two strings. So you can think of them maybe in the context of biology as consisting of these AC, GT sequences. And your goal is, given two such strings, compute the so-called edit distance between them, which you can think of as the smallest sequence of mutations that go from one string to the other. And you can get really into the nitty-gritty of things. So potentially you might encounter on one of your problem sets some question like the following. Maybe given the current win-loss record for every team in a baseball league, and given the schedule for which teams will play next in the rest of the season, figure out who in the baseball league is already out of contention for running for getting first place in the league by the end of the season. So these are questions that are, pretty down to earth. Like, I mean, ultimately, you can boil down this last question to, again, some question about graphs. And for these sorts of problems, one very important tool that you'll develop in your first year or so of study is the ability to work with, for instance, proofs, the ability to write down some mathematical statement and then rigorously justify that that statement is true. You'll also have to get comfortable with things like discrete math, like working with graphs, working with various things involving, say, combinatorics. Okay? But ultimately, these are the kinds of things that you'll end up acquiring the skills for after, let's say, your first or 2 years in CS. Okay? And really, this is kind of students' typical entry into this broader discipline of understanding, what are the ultimate capabilities and limitations of efficient computation. Okay. Another, topic that you'll quickly run into while you study things involving algorithms and also complexity theory is this fundamental tension between the kinds of problems that we would like to solve and this inherent limitation of what's sometimes called computational hardness. So it's a fact of life that we all encounter at one point or another, that there are certain problems that we would like to solve, certain algorithmic questions that are very simple to write down, but ultimately you realize if I only allow myself to run my computer for a reasonable amount of time, let's say certainly not on the order of like hundreds of years, certain problems just end up being impossible to solve because of that constraint on how much time you're allowed to run for. So a very famous problem in this vein, and maybe if people have seen things related to something called NP completeness, one of the first questions you'll encounter in this space is the so-called traveling salesman problem. So this says, roughly speaking, that if let's imagine I want to do some kind of road trip around the United States, and there are a bunch of cities or various destinations I want to hit on my road trip. And going from one city to the other, of course, there's some cost, right? You have to pay for a certain number of gallons of gas to get from city A to city B. And overall, I want to do this entire tour around the US that hits all of the different cities that I care about. And I want to plan out my tour in such a way that I minimize the total cost of traveling between all these different cities. Okay, so that cost could be measured in distance, it could be measured in the amount of gas, the amount of money you have to pay, what have you. And it turns out that this kind of question, if I consider in maximal generality, if I consider some arbitrary network of hubs that I have to transition across, this turns out to be what's called NP hard, or in fact NP complete. And within theoretical computer science, this is a class of problems that is strongly believed to be difficult in the sense that if I only allow my algorithm to run in a reasonable amount of time, I'm not going to be able to solve this problem. And by now, there's an entire zoo of different kinds of, not only different kinds of problems that are NP complete, but in fact, even an entire zoo of different so-called complexity classes that characterize just how hard a particular problem is based on the kinds of limitations you place on your computer. So there are limitations based on the amount of time that you allow yourself to run for. There are limitations based on, for instance, the amount of memory that you have on your computer, and more exotic things like the amount of randomness that your computer can generate, or even whether or not your computer is secretly a quantum computer. Okay, so these are all things that that people study in this discipline, and it's kind of one of the crown jewels within this idea that there is a difference between impossibility in the sense of there are problems that even if I ran in an infinite amount of time, I just can't solve, versus problems that are impossible to solve in a reasonable amount of time. The distinction between these two things is kind of one of the centerpieces of this whole area. Let's see another example. So let's say we take our favorite puzzle, let's say Sudoku. And okay, Sudoku typically is phrased in terms of putting the numbers from 1 to 9 in such a way that, okay, for every, as we know, for every row, we want all 9 numbers to appear. In every square, we want all 9 numbers to appear, in every column, etc. But you can naturally imagine scaling this problem up in difficulty. So, Sudoku problems are challenging, but ultimately they're things that we can actually get a handle on because there are only 9 numbers. But you can imagine, oops, sorry, you can imagine, scaling this problem up by increasing essentially the size of the grid. And this is again a problem that as the size of the problem instance increases, the amount of time that you need to run for in order to solve this problem becomes larger and larger. And this is, again, a problem where it's very easy to check for a given Sudoku puzzle solution, whether that solution is valid. But it's strongly believed that these kinds of problems are computationally difficult to find solutions for. Okay. Let's see another quick example. Let's say I'm trying to, again, I'm back to this map. But now instead of traversing different cities on this map, maybe I want to do the following. Maybe I'm just trying to draw this map and I want to assign colors to the different states in this map in such a way that no two states that are bordering get the same color. And so you could first ask, like, what is the fewest number of colors I need in order to color all the states while respecting this property, that no two states that border have the same color. Okay, and there's this famous result in mathematics that says that if I allow you 4 colors, then there always exists a 4 coloring of this graph. Okay, so if my question is just to determine for a given graph whether there's some way of assigning any one of 4 colors to each of the states while making sure this constraint is satisfied, the answer is always yes. There's always such a 4 coloring. Now, the remarkable thing is that, okay, you can scale this question down a bit. So maybe the 4 coloring question is, given the 4 color theorem isn't super interesting. So we always know there exists one. But in some cases, let's consider a more challenging problem where I restrict yourself to just 3 colors. And you can again ask, if I only have this palette of 3 colors, can I, fill in colors for all the states while having this constraint be satisfied? You can scale it down even further and ask, is it 2 colorable? And a very interesting thing happens here where if I allow you 2 colors, okay, in general, it is possible to determine whether or not such a 2 coloring exists. There's an efficient algorithm for this that I won't talk about today, but it's just based on kind of insights from graph theory. If you now go from 2 colors to 3 colors, you have a remarkable transition where with 3 colors, it's actually computationally intractable to determine whether a given map has a 3 coloring. Okay, so there are these kind of subtle hardness results that emerge when you transition between different regimes for your given problem. And this kind of distinction between 2 and 3 shows up in other areas of computer science. But this is just to give you a kind of flavor for the sorts of problems for which we kind of understand pretty well whether or not they're computationally tractable. Okay, so hopefully this convinces you that there is some fundamental notion of hardness within the study of algorithms, within the study of theoretical computer science. Let me tell you one more example, and this is one that maybe some of you have seen. And this is one that just involves arithmetic, so no more graphs involved. We can imagine the question of factoring an integer. Okay, so maybe my goal is I tell you an integer, I want you to give me its prime factorization. Okay, so I give you the number 21. Okay, what you would like to do is output 7 times 3. If I give you the number 527, okay, it's a bit larger, so you have to work a bit harder. But eventually you realize that the factorization is 31 times 17. Okay, but then you can continue this exercise. Every time you add like 1 extra bit to the problem, And at some point, the problem becomes quite challenging. So if I told you, please factorize for me this gigantic number, I don't even know what this factorization is. At some point I computed it on just on a computer, but this kind of question at least a priori it seems quite challenging. And this might seem like bad news because all of these examples I'm telling you are examples of computational problems where, if you only run your laptop for a reasonable amount of time, it would be hard to find the answer. But within theoretical computer science, there is this kind of long tradition of turning kind of lemons into lemonade. So even though we have examples of problems for which it's hard, you can get interesting things, like useful things out of this kind of thing. You can get, for instance, cryptography. So in fact, if you've seen these things before, the security of transactions on the internet actually hinges on the existence of hard to solve problems, on the belief that it's hard to, for instance, factorize large integers. It's certainly easy to check if I give you a candidate factorization for a number, whether or not that factorization is valid. But it's strongly believed that going in the opposite direction is actually, computationally intractable. Also, I noticed that just a second, I think my running low on battery. Okay, great. So this is already kind of one instance where a hardness result actually isn't terrible news, right? It says that you know if this is really hard, it actually allows you to, for instance, protect the security of online communications. Maybe just in the interest of throwing out like some fun fact, you can ask the same question not involving factoring, but involving primality testing. So instead of asking whether or not, or instead of asking, give me a factorization for a number, I give you a number and I ask, is that number a prime number or not? And you might think, well, like, factorization seems really, really hard. Probably it's hard even to determine whether an integer is a prime number. And one of the, breakthrough results within theoretical computer science was this finding that actually checking whether a number is a prime number can be done in polynomial time. So there actually is an efficient algorithm, albeit a very sophisticated one, that's able to solve this problem, even though we believe that factorizing numbers, on the other hand, is difficult. Okay, so these are examples of problems for which we seem to have a fair amount of evidence that there's hardness. And in general, you can think of theoretical computer science, at least classically, as giving some way of demarcating this entire landscape of different algorithmic problems. Okay, so here are just some keywords, but the specifics of the things that are on this map aren't super important for today's talk. But just to give you a sense for the breadth of this discipline, um, uh, one popular methodology for kind of understanding the limits of computation is to say, well, here is this entire sort of landscape of my favorite algorithmic problems. And I want to ultimately come up with some kind of classification saying that, these problems are hard and I have very strong evidence that I will never be able to find a clever algorithm that solves them. And on the other hand, these problems are easy and here are some, very beautiful algorithms for doing so. Today's talk is going to kind of break the mold of this. So instead of talking about these classic problems, many of which you'll encounter in your first or second year of undergraduate studies in computer science, I'm going to tell you about something that's maybe a bit more of a modern take on computation that still fits squarely within this discipline of theoretical computer science, and that's in the context of machine learning. Okay, so at this point, I'm going to switch gears. Are there any questions so far about what we've discussed? Great. Okay, so let's dive into some machine learning.
Actually, wait, I think we do have
Great.
one question in the chat. I think this was like a while back. I believe
Uh,
this is in reference to the traveling salesman problem, but
yes.
Victor asks, could I use AI to solve this problem by measuring how many ways you have and trying to predict whether or not a path will be the shortest one?
Yeah, so this is a great question. So uh, this is actually an active area of research. So first, let me mention that what does it mean for us to strongly believe that a problem is hard? Um, and this will actually segue into some discussion later on when it comes to machine learning. The kind of gold standard for what it means for a problem to be easy or computationally tractable in theoretical computer science traditionally is that if I give you any instance of this problem, I want my algorithm to work for that instance for regardless, even if the instance was kind of pathologically, adversarially constructed by nature, my algorithm should be able to solve it. And the unfortunate thing for traveling salesmen is that there exist problems, instances of traveling salesmen, namely particular essentially maps or graphs that you want to traverse, for which the problem is believed to be intractable, not just via the algorithms you learn in school, not just via AI, but basically via any efficient algorithm. And the alternative would be, if that weren't the case, then you would break, for instance, this long-standing conjecture that there's something called P is not equal to NP. So I won't get into the details of that. Okay, so it's strongly believed at least that there exist pathological instances of the problem, sort of worst case graphs for which this problem is actually genuinely intractable. But the question in the chat is great because people have, especially in the last couple of years, have started to question, whether or not worst case complexity is really the right way to quantify whether a problem is difficult, right? Because the kinds of instances of traveling salesmen that we might encounter on real world applications, they're not going to be given by some, pathological construction that someone, some theorist cooked up. They're going to be, real world maps. One popular line of work recently has been around sort of data-driven algorithm design that says that, well, if I have sort of a useful machine learning predictor like the one described in the chat, can I somehow use that as advice to inform the kinds of algorithmic choices that I make? And relatedly, what are, for instance, real-world assumptions on the underlying network that allow us to avoid computational intractability? In fact, this question I'll come back to at the very beginning of the third part of this talk. This is also sort of a core question, even behind what it means to formalize problems in machine learning through a theoretical computer science lens. Okay, so let's get back to that point, but it's an excellent, so the answer is basically on real world problem instances, you can indeed try to use machine learning to get better algorithms. Okay. Okay, so let me tell you briefly, how to think about machine learning in these theoretical contexts. Okay, so it's no secret that especially in the last like 2 or 3 years, generative AI has really kind of taken the world by storm. We now have amazing things. I'm sure all of us in the audience have used things like ChatGPT or played around with some of these image or video generation tools. And so this has really been kind of a major milestone in the development of methods in artificial intelligence. Let me try demystifying these methods a little and tell you kind of the bare bones recipe for designing these systems. Of course, the actual engineering and sheer financial and kind of computational resources that go into building these systems is considerable, on the order of billions or perhaps trillions of dollars to really make these things scale up. But the general recipe turns out to not be super scary. So at a very high level, you can think of these methods as ultimately trying to predict some kind of input-output behavior. In fact, at the heart of sort of the two main arms of generative AI, on the one hand, we have these things called large language models, which I won't formally define for you. And on the other, we have things like, for instance, Stable Diffusion, Midjourney, DALL-E 3, etc., these image models. They actually boil down to two specific kinds of prediction problems involving somewhat different input-output behaviors. Okay, so these large language models, ultimately, what are they doing? It's nothing more than the question of predicting the next word in a sentence. And so remarkably, I mean, these things seem very intimidating, right? Like how on earth do these ML systems work? And really the task that they're trained to solve is simply what's called next token prediction. So just next word prediction. So I give you some particular sequence of text, and I just ask you, okay, what is your estimate for what the next word in that sequence should be based on the prior that's been constructed through training on, let's say, the entire corpus of internet data. Okay, and that's the thing that drives all of these sort of state-of-the-art language models. What about these image models or these video generation or audio generation? It's a slightly different question. So instead of predicting the next word in a sentence, right, the input here is inherently going to be, a video or an image file. And here the prediction task is simply I give you a noisy image, okay? And the definition of noise isn't super important for this talk, but let's say I give you this noised up image of a pug. Your goal is to remove that noise. If you can remove that noise, it turns out you can do all these incredible things involving these AI generated images. Okay. So these are really the kinds of prediction tasks that drive a lot of generative AI. Okay, so now once you have this particular prediction task in mind, what you would like to do is first cook up an appropriate so-called architecture. So an architecture you can think of as just some family of functions which are in principle able to implement as rich of an input-output behavior as you would like. Okay, so one family of functions that maybe we learn in let's say AP statistics would be the family of linear functions. So let's say I'm trying to predict like a y value, so like how high up a point is, given the x value. One natural thing you could try doing is just fitting a line to your data points. Okay, this is linear regression, and so it's not a super expressive family of functions, but it's sort of a start. Okay? Once you get kind of deeper into the weeds of modern machine learning, right? The thing that everybody uses is deep learning, and at a high level, the idea here is you have certain building blocks that you can think of as layers in some so-called neural network, and each of these layers computes some rich nonlinear function of your data. And the idea is simply to stack together many of these layers. And one of the most popular architectures these days is something called a transformer. I won't go into the building blocks for what these neural networks involve, but at a high level, the idea is just I want to come up with some family of functions. It's parameterized by a bunch of numbers. These numbers correspond to so-called weights of your neural network. And if I pick the numbers correctly, I'm going to be able to accurately predict this input-output behavior. Okay, so that's what goes into picking an architecture. And kind of the remarkable thing is that this architecture, ever since like 2017, has kind of been more or less the same architecture that is the basis for all of these remarkable breakthroughs in generative AI. Okay, so this architecture, kind of the field has converged on this particular transformer architecture that's just done very well on a whole host of these kinds of applications. So once you've decided on your architecture, and all you have to do now is, set the parameters of your neural network appropriately to predict this input-output behavior. That's something that people will do using a whole host of heuristics. But at a high level, the method that they use to set the parameters of the neural network is through some kind of local search algorithm. So this is something called stochastic gradient descent. And at a high level, you can think of this algorithm as follows. Right? So first of all, this is something that if you want to implement at scale on a large amount of data, like if I literally want to train on the entire internet, this is going to cost a lot of money and a lot of computational resources. But the algorithm itself is actually not too crazy. Right? The algorithm is simply, you can visualize it as follows. So consider the following like landscape, where every point on this landscape corresponds to one particular setting of the parameters of your neural network. Okay. And so in this visualization, the lower the point is on the landscape, right? Somehow the better your set of parameters is. And so you just want to walk on this landscape until you get to the lowest point. And so what would be a natural way to navigate this landscape Well, you just keep going down, right? You want to get to as low of a point as possible, so just keep, trying to climb like further and further downhill until you get to kind of the basin of this region. And once you found the basin, that's sort of the optimal function from your family that would fit your data. And so for the kind of things that we learn in AP stats, like if I just want to fit a linear function, this landscape is always very, very clean and benign. And all you have to do is just, walk all the way down to the bottom and then you're done. Unfortunately, in the context of, these neural networks, you can write down a similar landscape, but actually it'll look very different. So instead of getting this nice, landscape where I just have to keep walking down and eventually I'll hit some basin, the landscape that you'll see for neural networks, and this is just some kind of visualization, um, is far more intricate in the sense that, well, it's not even clear if I just keep walking downhill that I'll actually reach the lowest point, the point closest to sea level, right? Because I might end up at some valley, and then there's no way for me to then keep walking downhill because I've reached kind of the lowest point in that valley, but not the lowest point overall in this landscape. Okay, and then, you could ask, well, if I get stuck in a valley, maybe I just like kind of wiggle around a bit. Maybe I climb a bit uphill and then try to restart somehow by adding maybe some noise to my system. And remarkably, somehow in practice, the fact that this landscape is super complex doesn't actually pose a problem. In fact, in practice, just by training these networks using this sort of hill climbing approach, you can get very good parameters that allow you to accurately predict this input-output behavior and get all of these remarkable behaviors that we see with state-of-the-art generative models. Okay, but that's the entire approach. So you just, you design some family of functions, and then to optimize over that family of functions in order to, find the best setting of parameters that would, best explain your data, you just do this very simple. I mean, the devil's in the details, but at a high level, you just do this kind of simple walking strategy. Okay, so that's sort of modern machine learning in a nutshell. And I have to say, as a theorist, I find it incredible that this kind of recipe actually works. In fact, this is one of the big open questions within my research area of designing mathematics that tries to understand how this is even possible. Because prior to the whole AI revolution, if one were to give a researcher in this area, a description of a landscape like this and say, okay, find for me kind of the best, the lowest point on this landscape, the reaction would be, okay, that's impossible. Like this must be hard. Like there's no way that we could build systems that can do this. And all the success coming from artificial intelligence tells us that for some reason, these landscapes actually aren't so bad. That you can actually find optimal values just by implementing the simple stochastic gradient descent procedure. Okay, so that's machine learning. At the risk of oversimplification, this is really at the heart of all the existing recipes for how deep learning works. Let me now say a bit about where theory fits into this picture, and this will kind of come back to this question of how to avoid the pathologies of worst case hardness that I talked about in the first part of today's talk. So what does it mean to do theoretical computer science for machine learning? Well, let's return to this map from before. I'm going to tell you a bit about how to think algorithmically in the context of machine learning. And there, instead of these problems like traveling salesman or sorting or these various other graph problems, the kinds of problems, I mean, you can write down an analogous map for problems in machine learning, and I won't go into any of the specific like points on this map. But it's entirely fair game to come up with similar algorithmic problems in machine learning contexts. And the only difference is kind of the sort of objects that you would study in machine learning versus in traditional theoretical computer science, like you would learn in an intro to algorithms class. So in intro to algorithms class, you might learn about the various things involving graph algorithms, maybe things involving scheduling, for instance, a collection of machines to perform a sequence of tasks. And maybe it involves certain things like what are called Boolean satisfiability problems. In contrast, in machine learning, the kind of first-class citizen, the sort of object that people all kind of hone in on, you can think of it as just some sort of black box. And this black box is just spitting out data. Okay, so imagine this black box could be, for instance, whatever process is generating all of the images on the internet, or maybe all of the, all of the threads on Reddit. Okay, it's just something that's generating data that your machine learning algorithm can then consume and try to deduce properties about that data. This data might, for instance, be the result of running some, scientific experiment or some clinical trial. This data might come from, for instance, customer data on some recommendation system. So, for instance, all the reviews on Amazon are ultimately generated through some process, some unknown process on the internet involving the various users of Amazon. And based on these reviews, you might want to deduce properties about, for instance, preferences across different populations of users. In fact, I would argue that it's even fair game to study questions that on the surface have nothing to do with machine learning, but maybe more to do with science. So for instance, another question you could ask involving, a black box that generates data is maybe you've set up some physical system in the lab and you're actually just, you're literally doing some physics experiment, and your experimental apparatus can shine, some lasers at some particle and get some experimental readouts. Right? That's also a example of some unknown process that's generating data. And so at the heart of all these different settings is a core question, which is if I have access to sort of snapshots of this process in the form of samples, in the form of data that's coming from the process, is there some way to then deduce properties of this process? Or, in the best case scenario, maybe we can just fully understand what are the general parameters that define this process in such a way that we can reproduce this process on kind of future data. So if I can really understand this black box that's spitting out data very well, then I could hope to potentially be able to simulate the process generating my data. And if you think about it, that's exactly what all this generative AI is really doing. It's saying, I've trained on all of the images on the internet, and now I'm able to, if I ask this model, give me an image of a penguin in a tuxedo, then it can readily do this. Okay, so that's really the key goal behind algorithms for machine learning. Given data, try to understand the process that generated that data well enough to be able to simulate that process. And this extends far beyond generative AI, even to scientific applications, to commercial applications involving recommendation systems. Yeah, the list goes on. Okay, so this is all fine and good. All right, you can ask similarly rigorous questions about these kinds of problems. Okay. But the issue is that whereas in the classical picture, with all of these, for instance, graph algorithms, traveling salesmen, sorting, etc., there we saw, okay, there are certain problems that are hard, right? They're maybe NB hard or even worse. But at the very least, there are also a decent number of other problems that are tractable, that for which we have sort of nice algorithms that have very strong guarantees. Well, what happens in the context of machine learning? Well, I would argue that the picture there looks more like the following, right? So if I look at any of my favorite machine learning problems, and I try to formulate them in a rigorous fashion, if I'm not careful about how I formulate that question, I can easily run into situations where that question just becomes totally intractable, right? But here we have to be careful about what it means to be intractable. So this goes back to this question in the chat, right? I can formulate these machine learning questions in such a way that let's say I want to get the same level of success that I got in the classical picture. So I want to say, given any particular instantiation of this problem, I want my algorithm to succeed. That is way too optimistic of an approach. And it turns out if I try to get that kind of guarantee, which sometimes we think of as a bound on the worst case complexity of the problem, most things, if you pose it in that framework, are going to be hard, right? And this is very different from sort of the classical picture where, okay, some problems are hard, but many others are actually, you can develop interesting algorithms. In machine learning, it's the opposite. Most things, if you're not careful, are going to be hard. And unfortunately, that results in this huge gap between what really seems to be possible in reality, on practical instances that people, care about, versus the kinds of settings that we can actually prove things about, right, as a theorist, right? And I would argue that this is not really an insurmountable gap. This is really just a limitation in how we think about the way that we pose these sorts of problems. And I think a lot of mileage towards understanding not just why methods in practice work, but also how to develop even faster methods, boils down to understanding the question well enough to formulate it in such a way that you can actually prove rigorous mathematics about it. So I would think this is sort of a glass half full versus half empty situation. You could think half empty in the sense that, okay, there's this huge gap. But at the same time, I think given the massive strides that people have made in the practice of machine learning, I think there's no better time to really start digging into these questions and understanding from a rigorous perspective why these methods are so successful. Okay, and so just like in kind of classical theoretical computer science, people really care about proving what we call upper and lower bounds. Upper bounds in the sense of just designing algorithms, and lower bounds in the sense of proving impossibility results, saying that, well, if I only have a limited number of GPUs or hours on my computer, I wouldn't be able to solve this problem. So those are still very central modes of thinking within this discipline. But I would argue a third and equally important mode of thinking that's that's extremely prevalent throughout the theoretical discipline for machine learning is the question of modeling, of actually formulating algorithmic questions that are both practically meaningful but also mathematically tractable. Okay, so this is something that if you in other areas, for instance, in physics and economics, this is largely the bread and butter of those disciplines of formulating interesting models where you can actually say things that are rigorous. And increasingly over the last few years, people have realized that a similar sort of approach is necessary for understanding machine learning. Okay. And finally, one meta point that I hope to make with this vignette, with which I'll conclude the talk, is that this is a lens that's very useful for understanding machine learning, but I think it's also a broadly applicable kind of skill set for understanding other domains. It turns out that this lens of viewing things as inherently algorithmic questions, for which you want to prove upper bounds on the complexity as measured by, let's say, runtime of your algorithm, this kind of lens is super useful, not just for machine learning, but even for understanding questions, let's say, in the social sciences and the physical sciences and beyond. So I'll say a bit about that in the last slide. Okay, so let me just check. How am I doing on time?
Yeah, you're totally good. We have sort of a break after this, so you can totally feel free to like eat into that if you want to. But as of
Okay,
right now, you're doing pretty good. So you have
okay, sounds
probably
good. So let me say a bit about the vignette. This part will get a little technical, but at least up to this point, hopefully, if people have questions, now would be a great time to discuss.
I actually do have one question myself. So,
Yeah.
as someone who's really wanted to sort of get more into computer science theory, what are some sort of things that you would recommend for just sort of starting to get into research and starting to get into like understanding CS theory? Because I think at least I don't know if I speak for everyone with this, but like at least coming in from like an outside perspective, I think a lot of it can look kind of like daunting and like a lot of the language can be very, like, very dense. And so what is your kind of approach for just sort of immersing yourself a little bit into like theoretical computer science a little bit?
Yeah, so I think getting into the kind of stuff that will prepare you, for instance, to take a first or second year class on algorithms is just comfort with discrete math and proofs. Um, and so uh, the kind of math that's needed is perhaps not super high tech, but what is really important to be comfortable with going into these classes is the ability to kind of just rigorously write down like a formal proof for a mathematical statement. So learning things like various proof techniques like proof by contradiction, induction, These kinds of things, I think taking a first year class on discrete math can go a long way towards getting one kind of prepared for this kind of thing. Um, I'll say that for machine learning like theory, actually another very useful skill set to try honing early on is just being comfortable with probability. I think probability is useful not just within computer science, but in a lot of other disciplines. Being able to start out and just understand, for instance, probability over, let's say, discrete objects, right? And then transitioning to probability over, let's say, continuous spaces. Being comfortable with that kind of thing, I think, is definitely crucial for getting further in terms of this machine learning space. But yeah, definitely, I think trying to hone one's like proof writing skills is probably the best starting point. I'll recommend a book near the end, which I think is also it's more in the vein of like sort of like popular science books written specifically for this discipline. But I think it's one that will get even without too much background, it'll help people get excited about this material. So I'll say more about that near the end. Yeah.
Absolutely. Thank you.
Okay, great. So let me now turn to the last part of the talk, and this will actually be neither about theoretical computer science, at least on the surface, nor about machine learning, but it's more about using this algorithmic lens that people develop for understanding machine learning from a theoretical perspective to actually say things about other disciplines. And so the discipline might come as a surprise to the audience, but that's actually I'm going to now talk about just optics. Okay, so but we'll see near the end how machine learning and theoretical computer science come into play. Okay, so the question here is very simple. So these are images of just stars in the night sky, imaged in pretty nice weather conditions through just a vanilla like classical telescope. And the thing I want to bring your attention to is this distinctive ring pattern that you'll see in these images. And intuitively, this ring pattern is you can think of as kind of taking your pinprick of light that's coming from your star and diffusing it so that it looks kind of blurry, right? So, for instance, you can imagine if I had these two disks, this is some binary star system, and I add this, this blur coming from this ring pattern. If I were to imagine these two stars coming closer and closer together, at some point, this blur might make it hard for you to tell apart whether you're looking at a binary star or just a single star. Okay, so at this point, like we've totally transitioned away from machine learning. I'm just talking about telescopes. Okay, but in any case, this ring pattern turns out to be a real thing. So it turns out that, anyways, I won't go into the technical details about this, but this is an actual kind of mathematical phenomenon that emerges just from the way like the diffraction of light kind of happens. So I won't formally define any of this apparatus, but really this will happen whenever you have some point source of light that gets passed through some kind of circular aperture. It's going to naturally result in this kind of concentric ring pattern. And this ring pattern is something called an Airy disk. And you can precisely pin down, mathematically what this disk looks like. Like you can write down for a given pixel in this image, I have an exact mathematical formula, which I won't define. Like this is some complicated looking equation, but it's something that you can really estimate for any given point on this plane through this formula. And this is something that people knew even back in the 1800s. So this guy George Beidel Airy was the first one to really write down this function that defines what this ring pattern looks like. Okay, and so the specifics aren't super important. I just want to emphasize that this is something that you can mathematically characterize, and it's not anything new. This is something that if you were to take a first or second year class in physics, maybe even in AP physics, you might encounter. Okay, and where does machine learning come into this? So I'm not going to design a machine learning algorithm per se for this problem, but I'm going to use the lens of machine learning and specifically of probability, as I mentioned, to get a handle on this. And so the first thing this is really just a shift in perspective. Instead of thinking of this as some kind of intensity pattern on your this observation plane in your telescope, instead you can think of this number, this k of x, which dictates the intensity, as simply the probability that a particular photon strikes that point on the plane. Okay, so now I'm going to kind of think of this mathematical formula that Beidel-Airy came up with as really describing a probability distribution. It's just, I have some random point and it lands somewhere on this plane, and the probability it lands there is exactly given by this formula. Okay, and so what is the problem I'm trying to solve? So as I alluded to, the fact that we have these concentric disks actually poses a tangible problem to imaging, in the sense that if I have two point sources of light, maybe two stars, or if I'm talking about microscopes, if I have two maybe cells and or structures on a cell which are too closely spaced, then the fact that I get this concentric ring pattern means that if I push them really close together, it becomes hard to distinguish that fine detail, right? And so, for a very long time, it was widely believed that this physical phenomenon of diffraction actually imposes a fundamental limitation to how well you can resolve this kind of fine detail. Right? Because of this blur that's coming from these disks, if I have two structures that are too close, I can't tell them apart. And so the conventional wisdom, that you would learn in a first year course on optics is that if you have two disks that are too close to each other, then this blurring makes it actually impossible to distinguish them. Okay, so as a theorist, I like, formal definitions. So my question is, how close exactly do you have to get before these two disks become impossible to distinguish? And this is a question that's kind of haunted, I guess, classical optics folks for, over a century. And the specific definitions aren't super important for this talk, but suffice it to say that many different physicists have proposed different criteria for how close two disks have to be before you couldn't tell them apart. One of the most famous ones that's taught in textbooks is this Rayleigh criterion. Okay, and it's some condition, like if the disks are too close by this margin of like 1.22 times some parameter, okay, then they claim that this is the point at which it becomes impossible to tell whether you have, say, two stars or just one star. And so, there's all these different proposed criteria. Which one is actually the real one? And this is not just an academic question that we pulled out of thin air. This is something that's been debated by physicists over the years. Interestingly, Rayleigh himself, when he proposed this criterion, said this rule is convenient on account of its simplicity, whereas others tried to push through their own criteria by saying it is obvious that their criteria should set an upper limit, and then they justify this by saying my own observations on this point have been checked by a number of friends and colleagues, so it's kind of like a proof by intimidation. And then you have remarks from folks like Richard Feynman, who said these kinds of limits seem a little pedantic. And he even says, if you make sufficiently careful measurements of the image, then you can tell apart two points, no matter how close they are, even below any of the limits that people have proposed. So there's even this kind of lack of consensus on whether the diffraction limit is a real thing or not. And so the nice thing about viewing all of these from the perspective of theoretical computer science will be that we can actually give a rigorous resolution to this question. Okay, why is this important? Well, there have been entire Nobel Prizes awarded for kind of circumventing this so-called diffraction limit. Right, there's substantial, despite this impression from Feynman and others that maybe this is just a pedantic question. Experimentalists, especially in the context of using microscopes to image small systems, they've run into this issue where you can't really resolve this fine detail using just a off-the-shelf microscope. And in fact, 10 years ago, the Nobel Prize in Chemistry was awarded precisely for the development of new technologies that allow you to surpass this limit. So this suggests that, given that you had to invent an entirely new kind of microscope to circumvent this limit, there has to be some truth to this limit. Okay, and so I think in the interest of time, I won't go into the specifics, the mathematical specifics, but at a high level, by leveraging insights from actually machine learning theory, where we often study questions about learning parameters of a probability distribution given access to samples, you can entirely cast the question of resolution as a machine learning question, and specifically as an algorithmic question for which you can say rigorous mathematical things about that model. And let me just skip to the punchline. What we find is that the difficulty of diffraction really emerges only when the number of point sources of light is large. And in particular, in situations where there is a small number of close by sources, for instance, in astronomy, right? If I only care at most about like 2 or 3 stars at worst, it is actually possible to resolve below the diffraction limit with an efficient algorithm. But in domains where there are many close by sources, for instance, if I'm looking at a context where I have to use a microscope and there's a lot of kind of fine detail that I have to resolve, many different neighboring cells, then diffraction really does impose a fundamental limit. We show that it's the amount of data that we need, the number of photons we need to strike this observation plane has to scale exponentially in the number of sources. And so at a very high level, our work shows that this physical phenomenon, this diffraction limit, can actually be understood purely as a statistical phenomenon. The technical word for this is a phase transition in the sample complexity for this task. But long story short, it's we're casting this physical problem as purely a question about machine learning. And hopefully this convinces you that this general algorithmic lens on not just on computing, but on data science specifically is broadly useful. It's not just about understanding machine learning. It's really about using insights from statistics and from algorithms to say new things about problems that people in other areas care about. And I find this particularly exciting because this is one example where there are all these different fields. On the one hand, there's optics. On the other, there's people in my neck of the woods who work on machine learning, and there are also various other related communities in signal processing. And it turns out that all of them have secretly been studying the same thing. In fact, the main tool that we used to prove this result was some mathematical machinery from analytic number theory. Okay. And so I find it especially exciting when there's this kind of when different researchers are actually, unbeknownst to each other, working on the same mathematical object. Okay, so that's all I wanted to talk about. Let me just say, and this is the book that I wanted to kind of pitch to folks. There's this excellent book on mathematics and computation by Avi Wigderson, who's kind of one of the giants in this area. And this book, and more generally, kind of the progress in theoretical computer science over the last few years has shown us that if you take this kind of computational viewpoint, where you phrase things in terms of how many computational resources do I need in order to solve a particular problem. For instance, what can I do with a programmable computer that can run for only a reasonable amount of time? That viewpoint has actually really transformed the way we think about not just algorithms, but a bunch of other problems from other disciplines. So I told you one example from optics. Some other success stories. So within, for instance, physics, this computational perspective has really revolutionized for instance, our perspective on things like statistical mechanics. If I look at sort of interacting systems of particles, the onset of computational intractability actually tells us precise changes in, you can relate them to precise changes in phases of matter. Also, a natural place where computing is relevant is in the understanding of quantum computing. And even, in the last few years, people have already started to build, real world quantum computers, albeit ones that are quite limited in capability currently, but it's a very exciting time for that area. Within the social sciences, there are things like algorithmic game theory, algorithmic fairness, and privacy. How do I release, statistics about a population while preserving the privacy of every individual in my population? Computational social choice, what are the best ways to organize sort of voting systems to ensure that certain societal outcomes are satisfied? Interestingly, even within sort of pure mathematics, a lot of the tools that people in theoretical computer science have developed have paved the way to resolving long-standing open questions there. And so there's this nice kind of synergy between, on the one hand, pure like mathematical statements that have nothing to do with algorithms, and on the other, questions that inherently are about computation. And maybe as one last pitch for why I really like theoretical computer science, there's the sense in which it's tackling questions that are fundamental philosophical interests. So one area that I haven't had time to talk about is there's this, long research program on understanding the role of randomness in computation and whether or not it is actually inherent, essential to getting certain fast algorithms. And you can phrase this entire question of whether P is equal to NP, which I haven't formally defined for you today, but is one of the centerpieces of complexity theory. That's ultimately a question you can think of as, is creativity something that you can actually automate? Okay. So, lots of questions to explore in theoretical computer science and lots of areas that it touches upon. And I would argue that especially with the advent of all these amazing successes in generative AI, now is really one of the most exciting times to get into this research area. So if you're interested in learning more, please feel free to reach out to me and to take a look at this book because I think there are a lot of interesting open questions in the coming years for people to work on. All right, so that's it. Happy to take questions now.
So I have a question. Um, do you have any suggestions in terms of whether it be research or software or just further reading or any even programming languages in regards to further studying and going deeper into the intersection of machine learning and like computer vision and image data analysis?
Yeah, so this is a question I get a lot from my students. So um, I think unlike other academic disciplines where there are concrete textbooks that people will just point to, within machine learning the field moves so quickly that honestly textbooks often are fairly outdated when it comes to understanding the latest and greatest methods that people use in real systems. So I would suggest there are tons of useful, for instance, even YouTube channels that go over that do deep dives into papers. There are, a lot of interesting blog posts that give tutorials on kind of the methods that people use. So I honestly just Google is your friend and just if you encounter like blog posts about some latest and greatest method, let's say you want to learn about what is a transformer, what is self-attention, uh, what is for instance, what is a second order method in optimization. These things, if you Google and you look at kind of the top blog posts, they actually give very good overviews on these sorts of things. So it's kind of an unconventional answer in the sense that people expect that maybe there are like nice books for this, but yeah, I recommend this. Another resource that I would suggest is there's this YouTube channel that the Simons Institute runs. So this is a research institute based in UC Berkeley. Um, so most of their content has been more on kind of the theoretical computer science end of things, but especially over the last year or so. For instance, this year they're having a special year on specifically on large language models, and they often invite kind of top researchers in these areas to give, for instance, keynote lectures. All the content there is publicly available, and I would highly recommend taking a look. So yeah, those are my suggestions.
Yeah, I think we got a question from the chat. So I think this is sort of getting at just sort of generally, we heard a little bit from Dr. Taylor about like CS and pursuing some projects. And I think people here are like generally kind of familiar with, pursuing like computer science as it relates to going into industry and everything. But Eva asks, what kind of jobs does this career field sort of provide? And what does employment look like for someone who's sort of studying like theoretical computer science?
Yeah. So I think the obvious answer is that certainly one route is going through academic research, but increasingly I think there's this nice interaction between academic research and industrial research, specifically as related to machine learning. Um, so I think there's a strong demand for candidates that are able to certainly, one kind of superpower is, being really great at coding and kind of on the engineering front. This is an entirely orthogonal skill set that obviously is highly in demand. Um, but in many cases, what people want is some mixture of that with the ability to kind of think rigorously, or at least be able to understand the basic building blocks from a mathematical perspective for how these systems work. So I think, even short of going into like a full-blown career within theoretical computer science, being able to kind of navigate that kind of fine line between, on the one hand, the the kind of the black magic that goes into implementation for these systems. And on the other hand, having a deep understanding of the mathematics, I think, can take you a long way. And it kind of allows you to kind of wear many hats at once. So I would say that when going, for instance, going into undergrad, I would recommend taking these classes like Intro to Algorithms, not just because the material is cool, but also from a practical perspective, it certainly helps when it comes to getting you prepared for, let's say, tech interviews that involve, coding assignments for better or for worse. But at the same time, it also gives you this rare skill set of being able to like precisely define what exactly is the problem that your methodology is trying to solve, and in particular, being able to decouple the algorithmic problem from the algorithmic method. So this kind of clarity of thought, I think, is something that it's great to develop early on, and algorithms classes is definitely one great way of doing that. I think related to the industry positions, also there's in the area of AI safety, there's been this increasing like interest in being able to design generative AI systems that are controllable or that we can actually understand the inner workings of. And so there's, for instance, been a lot of work in recent years on something called mechanistic interpretability, where try to turn a microscope to the actual weights of the neural network that you've trained, and try to see, okay, does this particular subnetwork of your transformer encode some particular like functionality, and can I actually like literally interpret that? These kinds of positions, which are kind of at the intersection between industry and academic research, I think for that it's definitely very, very helpful to have some mathematical some theoretical training going into such positions. So that's maybe to give you a sense for where this is useful.